Hi! Today I'm going to talk about standing waves. So these are waves where you have to shake your slinky. I should have brought a slinky. Shake your slinky, and then you can get these patterns of up, down, up, down, up, down. So they're standing waves as opposed to traveling waves. Traveling waves are just the wave pulses that move along like a wave on an ocean. Standing waves are on a fixed distance, fixed length of slinky. You can have a standing wave in sound. And so we've got this pattern of up, down, and they're quite beautiful. And I'm going to show you how to work with a bunch of different types of standing waves. So the first one we're going to deal with is a closed system. So closed means the two ends are fixed. And this is something where we'd have a slinky or a string. And we're going to have a pattern of standing waves on something where the two ends are fixed. And this is when you're shaking your slinky, this is what you have, is a closed. So strings and slinkies, always closed for everything that we're going to do. So what would a standing wave look like? Well, the simplest standing wave, which we call the fundamental harmonic, is just going to be a one football shape. Not very symmetric, but hey. So one football shape. Closed means that the two ends are fixed and the string isn't free to move. But in the middle, the string is free to move, and so we've got this just up, down motion. We have special words for the two ends and for this middle bit, and those are words that you will want to remember. So this is a node where there is no motion. That's how you can remember it. There's no motion. So the nodes are where it's fixed ends. And this point right here in the middle, where we have our maximum motion, that's an antinode. Anti being opposite of node. And the way I can remember that is that's where we have our maximum amplitude. So a node is where there's no motion. An antinode is where there's a lot of amplitude. So this is our simplest closed standing wave. This is our fundamental harmonic, our first level. And we can kind of come up with some ideas about this if we know the length of the slinky or the string or whatever. We can also figure out how that length and the wavelength relate. So I'm going to draw the first three harmonics of a standing wave on a closed system. So we have to have closed ends. The simplest is always just one football shape. The next simplest is going to be a two football shape, so up, down, up, down. The third is going to be three football shape. Pretty easy to remember. Closed is a nice easy one. So it's just one footballs, two footballs, three footballs. And then we've got a node and an antinode and a node. So each time we go up, we're increasing the number of antinodes and increasing the number of nodes as well. Now we had defined a wavelength earlier, and we had defined the wavelength as a peak to peak distance. So one wavelength is the distance from peak to peak, or the same thing, it's trough to trough. So if you look at the set of three here, can you see how much of a standing wave makes one full wavelength? So if we have peak to peak, how much of what kind of standing wave is that? So here I'm going up and then down back to center, but I'm not getting back to center having gone the full wavelength. Here I'm going up and then center and then down, and now I'm back to normal. Here I'm going up, then down, and back to normal, and then up again. So if you kind of compare what a wavelength is to these three pictures, hopefully you can see that this right here is one wavelength. So a wavelength on a closed system is two footballs. And that's a good thing to remember. One wavelength is two footballs. Kind of weird language, I know, but that's a football, right? So we've got a wavelength here, and if we have a known length of the slinky, we can figure out a wavelength to length relationship for each type of waveform on this closed string, or slinky. So if 2 footballs is 1 wavelength, then for a second harmonic, the wavelength is equal to the length. For a first harmonic, how much of a wave is 1 football? Well, if 2 footballs is a full wave, this is a half of a wave. So for the first harmonic, we have the length is equal to half of a wavelength. And then we can go up to the third harmonic. So for the third harmonic, can you see it? Try it. Stop right now. Go. Try it. Hit pause. Okay, did you try it? Good. So for here, I have the known length, and in this known length, I have 1.5 waves. So 3/2 waves. You can rewrite these if you want to have the wavelength equals 2/3 of the length. So just flip the 2/3, the 3/2 over to the other side. And again, that should make sense because the wavelength is 2 out of the 3 footballs. So the wavelength is 2/3 of the total length. Here, we could write the wavelength as 2L because to get a wavelength, we need 2 footballs. So if we have a length, we need to double it to get 2 footballs. So this is something you're going to need to be able to do on your own on an assessment. Be able to draw what the waveform is for the particular harmonic, first, second, third, and now it goes up. This one's really easy. Fourth is just 4 footballs. So 1, 2, 3, 4. So the fourth harmonic, I see in that length there are 2 full waves. You can do the fifth, the sixth. So on an assessment, you'll need to draw what the waveform looks like and be able to come up with this relationship between the length and the wavelength. So that's the basic system for a closed standing wave. Now we also have other types of standing waves that we can do. So what if the ends are not fixed? What if we're not dealing with a slinky or a string, but we're dealing with, let's say, a whistle? So a whistle is an open-closed system for standing waves. So one end is open, if you think of just like a recorder type whistle, this end's open and this end you're blowing in it, but that end is fixed. So this means we have an antinode on one end and we have a node on another end. So if you can imagine what that looks like, try to come up with what the first harmonic, the fundamental harmonic, would look like for a standing wave for open-closed. So the first harmonic for open-closed. It's got to have a node on one end and an antinode on the other. And the fundamental harmonic is always the simplest way to get from one to another. So, you can kind of use these as a guide. What would be the simplest waveform for open-closed, just going from a node to an antinode? Well, if I look at that, node to an antinode, it's just this much of the wave. So the first harmonic for open-closed is half of a football. So there's our first harmonic. And we can have a second harmonic. And now this is the next simplest way to get from a node to an antinode. So if I'm starting with a node, okay, there's my first harmonic. I need to go to an antinode. So it's not stopping there. That's a node again. I have to go all the way to an antinode. So here's our second harmonic, and our third harmonic would be one more shape. So there's my second, that's a node, that's my next antinode. So here's the first, second, and third harmonics for an open-closed wave, open-closed standing wave. And you just have to remember, open means an antinode, closed means a node. So we've got our node, antinode, node, antinode. Same thing here. Node, antinode, node, antinode, node, antinode. Now we can do the same trick with the length to wavelength relationship. So there is a certain length of this whistle, for instance, or a flute, and how much of a wave is this? So in that length, how much of a wavelength is there? This is still true. That doesn't change just because we're now dealing with open and closed. I mean, we're just dealing with part of a big waveform. So if one wave is 2 footballs, How much of a wave is half a football? It should be 1/4 of a wavelength. So for the first harmonic, open, closed, the length is equal to 1/4 of the wavelength. Or you could say the wavelength is 4 times the length, because we'd need 4 of these, 1, 2, 3, 4, to get 2 full footballs, to get a full wavelength. All right, so right now, hit pause and, well, okay, after I tell you what to do. So you're going to figure out what the length-wavelength relationship is for this one and this one. Okay, hit pause, give it a try, see if you're right. For the second harmonic, we have a certain length. We know what the length of the whistle or flute is. And this is 1.5 footballs. So 1.5 footballs is 3/4 of a wavelength. So for the second harmonic, the length equals 3/4 wavelength. And here, again, we have our standard length. And now we have a full wave. There's my full wave. So I have a full wave plus 1/4 of a wave. 1 1/4 or 5/4 wavelength. So for the third harmonic, the length is equal to 5/4 of a wavelength. So 5/4, 3/4, 1/4. So it's a nice pattern there. It just goes up 1, 3, 5, 7, 9, 11, 13. And it's a little bit different, you see, than the closed. So it's the same process, but you come up with a slightly different answer because we have not the same amount of footballs. So there is a third type of standing wave. You can probably guess what it is. From closed, closed, open, closed. We're going to do open, open. So an open, open is going to be something like the boom whacker tubes that you may have seen. If you look up boom whacker, they're really fun. I'll show them in class. And sometimes you can have whistles that are open on both sides. So open, open. A lot of organ pipes are made open, open. So open, open. That's our third type. All right, so open, open. This means we need to go from an antinode to an antinode. Antinode to an antinode. So let's look and see what's the simplest way to get from an antinode to an antinode. So the fundamental harmonic, the first harmonic, is always the simplest way to get from antinode to antinode. So there's an antinode. The simplest antinode next is just that. So it's going to be this part of a wave. So we're going to start with an antinode and go down to the next antinode. So it's going to look like this. So there's our first harmonic of open, open. So here we only have one node and 2 antinodes. So first harmonic. And if we have that length, are you good enough to see it now? How many footballs is that? Well, it's a half a football plus a half a football. That's 1 full football. 1 full football was half of the wave. So this one looks like that. It's the same equation, even though the picture's slightly different, the equation ends up being the same. Second harmonic is the next simplest way to go from an antinode to an antinode. So I'm going back up to the top antinode. All right, so there is our second harmonic for open, open. And I'm being a little sloppy here, but hey. So can you figure out the length to wavelength relationship? Give it a try. There's a half a football plus 1 football plus a half. That's 2 full footballs. You should end up with length equals wavelength. Same as here. Third. And all right, so antinode, there's my first, there's my second, there's my third. Okay, so this one, again, the pattern just keeps on repeating. If I asked you to do the 6th harmonic of open, open, you can just keep going along. And for the third, it's going to be the same thing as this. Open, open, and closed, closed have different pictures, but they have the same equation. So for the third, we have the length equals 1 1/2 wavelengths, 3/2 wavelengths. So that's the process for figuring out what type of standing wave you have on a 3 different types of strings, or media. I guess I'll call it media. Typically open, open, and open, closed are going to be things in air, whereas a closed, closed is going to be a slinky. So anytime you have a wave on a string or a slinky, I'm treating it as a closed. Otherwise, I probably would tell you it's an open-closed whistle, or it's an open-open organ pipe. But if it's a string or a slinky or something like that, a wire, go with closed. So this is the basis of the standing waves, and I'm going to close this video off, then do another video with a problem, showing you how to solve a problem with standing waves. All right, good job.